In a universe where physical resources are finite and time is irreversible, how do we measure the infinite potential of a computer program? Measuring speed in seconds is a lie. It tells us about the hardware, not the code. To understand the true cost of computation, we must abandon the stopwatch and enter the realm of asymptotic geometry.
Imagine a physicist measuring gravity, but their stopwatch runs at random speeds depending on the weather. That is the state of empirical computer science. A fast algorithm on a slow machine looks identical to a slow algorithm on a fast machine. To separate the nature of the code from the nurture of the hardware, we need a standard of measurement that ignores the machine entirely. This leads us to the invariance thesis. It states that all reasonable classical models of computation, like a Turing machine or a random access machine, are polynomially equivalent. This means a problem solvable in polynomial time on one is solvable in polynomial time on the other. While moving between these models might square your runtime, changing linear time to quadratic time, the problem remains tractable. Crucially, within the same model class, Big-Theta absorbs hardware speed differences as irrelevant constants.
To map this trajectory, we use three specific tools. Big O gives us a ceiling. It guarantees the code won't be slower than this. Big Omega gives us a floor. It warns us the code requires at least this much work. But Big-Theta? Big-Theta is the corridor. It confines the function between a floor and a ceiling that grow in perfect lockstep. While the numerical gap widens as inputs grow, the rate of expansion is identical.
Mathematically, this is a sandwich. We say a function f of n is Big-Theta of g of n if we can squeeze it between two multiples of g. Specifically, constant 1 times g of n must be less than f, which must be less than constant 2 times g. Crucially, this inequality must hold for all n greater than a specific threshold, n0. We strictly ignore the initialization phase and startup costs of small inputs to focus purely on the long-term growth rate.
We manipulate these bounds using cost function algebra. It follows rigid rules. If you have two steps in a row, you add their costs, and the larger one dominates, erasing the smaller one completely. If you have a loop inside a loop, you multiply their costs. And crucially, if you simply speed up the processor, multiplying the speed by 100, the notation absorbs it. Asymptotically, 100n is identical to n.
Not all algorithms submit easily to this exactness. Merge sort is rigid. It divides blindly, meaning its cost is unconditionally theta of n log n. Pure quicksort is volatile. If you pick a bad pivot, it degrades to theta of n squared. It is worth noting that modern production systems often use intro sort, a hybrid that switches to heap sort to prevent this crash, but the pure algorithm remains theoretically conditional.
Why do we obsess over the limit as n approaches infinity? We will never process infinite data. We do it because the limit is the only place where the noise fades away. In the limit, the messy reality of cache misses and clock cycles vanishes, leaving only the pure Platonic structure of the algorithm itself.
This is the ultimate utility of Big-Theta. It is a filter for truth. It separates the accidental properties of the machine, which change every year, from the essential properties of the logic, which remain true forever. It is the bridge between the messy reality of silicon and the pristine certainty of mathematics.